Hi, grade 9s. Today I'm going to take you through 7.7, which is the last portion of Unit 7. And we're going to be looking at identifying types of symmetry on a Cartesian plane. A Cartesian plane is just a sort of a mathematical fancy way of saying this XY grid that we're so familiar from, say, our unit on linear relations, unit number 4. We often taking values from an XY graph and then plotting them on Cartesian plane to see if we could find lines, relations between two separate values or expressions. If we had linear relation, remember all the points lined up and we were able to connect them sometimes, and sometimes we had to leave them as dots. In any case, we used a Cartesian plane for that, so it's just the big old XY grid. And we've dealt with rotation and angles of rotational symmetry for objects where we're spinning them around a central point. And what we're going to look at in Unit 7.7 is how do we look at objects and the way that they can be rotated or the way that they can be reflected when it comes to a point that's outside of the original object. So that's sort of the new concept that we're dealing with here on 7.7. And there's a couple tips and tricks that I'm going to get you to use just to help yourself work with this for the quizzes and for the exams. This is one that this is a concept that people who are very good at visualizing objects have very good, clear mental pictures about how objects can rotate and be spun and reflected in space, tend to just kind of be naturally good at. And if you are that person, that's great. You probably have to do a little less work. If you're not that person, that's fine. There's still a process. There's still a series of steps that I want you to go through to make sure that you're able to understand if objects are symmetrical, either by a line or by being able to rotate those objects. So let's look at both of those concepts here. The first one is rotational symmetry, and we've talked about rotating objects before and angles of rotational symmetry. But if we're looking at an external point here, external point being outside of the original object, so if A is the original object, and I think it might make sense for me to label these corners as well, because that is an important part of what we're doing right now. Let's call that A. Sorry, line's a little thick. Okay, so we'll call this point A, not A prime, just A. This will be B. This point will be C, and this point will be D. And we're just going to look at where the points are on the original object and where they end up on the new object, which is B. It's asking us for this first part to rotate 180 degrees about, and that's basically around, point E, which is at -1, 2. Remember, that's always the X value, that's always the Y value. It goes in alphabetical order. Now, what happens when we take every point and translate it transform it over a 180 degree angle? Well, 180 degrees is a straight line. All right. Now, if we just look at a sort of a traditional Cartesian coordinate system here, if we have a line that starts out right there and then rotates 90 degrees counterclockwise, okay, so that would be a 90-degree rotation. If we do another 90 degrees, we end up at 90 plus 90, which is 180 degrees. And you see how that's a straight line, right? So this represents 180 degrees. If you go one further, if you go another 90 degrees, you end up at 270 degrees. I don't know why I wrote 207. 270 degrees. That would be straight down. And if you go back to the top, you've really rotated. You've either started at 0 degrees or you've rotated 360 degrees, which is one full revolution. So we just need to keep that in mind when we're rotating. What do these angles actually look like? Okay, so a 90-degree angle is going to be looking like that, and a 180-degree angle is going to be a straight line of some type. And then those are probably the only ones that you're going to need to worry about in this unit. As you move a little further into geometry, you're going to learn how to rotate things by different angles and more complex angles like 30 degrees or 60 degrees, a lot of 45-degree increments, things like that. But for now, let's just worry about flipping things and rotating things 90 degrees or 180 degrees. Because the 360-degree revolution ends up exactly where you started, you don't have to worry about that one. Okay, now here's how This is you'll be able to determine if there's rotational symmetry. And this is the process that I always use. Okay, we're going to start with 1 point on the object, and we're going to start with B on this one. And then you need to draw a line from B to whatever point it is that you're trying to rotate around. Now, it told us to rotate around point E. So if I draw a straight line from B to E, okay, that goes basically from here through that line to the E. But you could also consider that if to get from point B to point E, just moving left, right, and up and down, you could bounce over 1 time, 2 times, and then down 1. Okay, so point B can go right, so 2R for 2 right, and then 1D, which is down, 1 down, and we get to point A. So point B goes 2 right and 1 down to get to point E. Now I know that point B has to be in a straight line somewhere, okay, on a straight line somewhere on the other side of E. So the only way that I can put it on a straight line is to just continue that black line through here. So it's got to be somewhere in this direction, right? Because that's a straight line, 180 degrees. But where exactly does that point end up on the new rectangle? Well, you can see the green rectangle. They've already drawn it in for us. But you'll notice that if we do the exact same thing again, if I go from point E, and I use the exact same process, and I go 2 right and 1 down, I get to the correct spot. So if I go 2 right, that's 1, 2 gets me there, and then 1 down gets me to there. That's where I need to end up. Okay, so I'll just kind of get rid of these just so that they're out of the way. But you'll notice that the steps I use to get from B to E, and if I use them again, they will get me to my new B position, which we have been in the habit of calling B prime. And we should continue to be in the habit of calling B prime. Now, once you have that single point, if you're sort of a good visualizer, you can imagine what's happening for each of these points, that may be enough for you. But I do want you to sort of get in the habit of drawing 2 points in order to make sure that everything is lined up properly. Because it's one thing to get the correct shape in the correct spot after rotating it. It's another thing to make sure that you've got your points transformed or in the proper spot on the new version. Okay, because the points and the lines that connect each point need to be exactly the same. Nothing can change there. So let's look at point C, and maybe I'll do point C in red. Okay, how do we get C to E? Now we could draw a straight line to E and then just continue that straight line, and we're pretty sure where that's going to end up. That's going to end up right there. But let's also try bouncing from point C to point E and see what happens. So if we go 1, 2 toward the right, and then 1 up this time, so from point C, if we go 2 right, but 1 up instead of 1 down, I get to point E. So then I go from point E. If I just repeat that, 2 right and 1 up, watch what happens. So from point E, I'm going to bounce 1, 2 right, and then 1 up, and I get to exactly the point that I thought I would get to. And we could continue doing that with each of the points. But really, once you've got 2 points, especially if it's a rectilinear object, it's only got 4 corners. If I've got 2 corners, 2 of the 4 corners, I know the rest. If we look at A, we know that A has to be connected to B on the long side, and it has to be connected to D on the short side. Well, there's only one place that can possibly be on our rotated version, and that is if A is connected to D and B, the only place it could possibly be is right here, because it's connected to B, and this has to be D. The reason that both of those have to be in that spot, if you just kind of combine them together, you know that D has to be connected to C. The only place that B can be connected to, or D can be connected to C, the only place that that can happen, because we already know where C and prime and B prime are, the only place that it can connect to D is right here. So that has to be D prime. And you know what? The same logic follows for C. C has to be connected to B, Okay, so sorry, A has to be connected to B, which means that the only place that you could put A would be right here, A prime. That's the only place you can put it that it was going to be connected to B. And then just for a double check, it also has to be connected to D. So A is connected to D on the original, A is connected to B on the original, connected to B, connected to D. And you can check every point. C needs to be connected to B and to D. C is connected to B and to D. So by just tracking a couple of points over to the new version, you can be sure that you're going to do this reflection appropriately and properly. So that is rotational symmetry. That demonstrates all those steps I just took, that this object does indeed have rotational symmetry. There is a way for me to rotate it 180 degrees, or the object B is representative of a 180 degree rotation, which means it does have rotational symmetry. Another way that you can do it, and this is sometimes depending on where the object and the line that you're asked to, or the point that you're asked to reflect, as long as those are situated in a relatively straightforward manner, you could actually use just a line method to visualize it, and I think it makes it a lot easier sometimes. So I just drew a little black line there. Okay, all I did was draw a black line right there that connected the center, okay, the center of the object. Now I'm just going to relabel it quickly here. So that was A, B, C, D. So I said that this BC line, the middle of that can very easily be in a horizontal manner. And when you're doing these lines, you always want them to be either horizontal or vertical. You don't want to be on an angle. That makes it a lot more difficult. You can still do it, but it makes it more difficult. It's very, very easy for me to draw a line from BC to E. And what it does is it makes kind of a bigger shape that I can use in the meantime. And I'll just highlight what that bigger shape might look like. So let's just pretend that my original rectangle, this box here, let's just pretend it had a little stem, a little branch that connected it to that E point that we're using to rotate. Now it becomes easier for us to picture a rotation of this entire object 180 degrees. So that little stick that I joined there that the blue line's pointing to, if I just put that the other way, 2 units, because it took 2 units to get to the E point, so I'll make 2 more. And right there, it's very easy for me to visualize that this whole object, the A point had to flip all the way over and it's going to end up over here somewhere. So it becomes very easy to see that this must be where my A prime is, and this must be where my D prime is. Okay, and then if this is the stem, and the whole thing flips over, the B actually goes past and down, so that right there has to be, that was B. This flips around. Yeah, that's got to be B prime. And, oh, I did my A, that's why I was looking weird. Sorry, my A got a little messed up there. The A has to go all the way up and around, all the way down to there. I don't know why I labeled that D. Sorry, that's my A down there. Okay. And you can convince yourself of this by, and then the C prime and the D prime. Now you could convince yourself of this if you really wanted to. You could just cut a little piece of paper, and then I'm just going to group these together for a second here, and then watch what happens when I spin it. Where's my group? This line. Group, there it is. Okay, now watch me rotate this, okay? So just pretend it's kind of like the wine glassy thing. So I'm rotating it, and then I know that's 180 degrees. I flipped it, and then this dot had to end up right there. Okay, now look at how it lines up. It lines up perfectly with that. Now, the only thing I'm missing when I did that rotation is I need to connect one of the letters just to convince myself that it's moving the way it's supposed to be moving. So I'm just going to take this A point, and I'm going to join that to this object so that when I spin it, I can actually see where the A the A point is ending up. So when I flip this over 180 degrees, which is upside down, and I make sure that I put that E back at the original E, you can see that the blue A ended up on A prime, which is where we thought it should end up. So just by me sort of taking my notebook and spinning it around while holding my finger on that A point is really all that I did. I convinced myself that I made the right choices as to which points need to end up in which place. A prime, D prime, C prime, and B prime are all in the right place. So you can either track a couple of points using the first method, or if it's lined up nicely, and let's get rid of everything, it looks a little cluttered. If it lines up nicely, whereby you can just draw one line from the middle of one of the lines and make sort of a visual representation of that object for yourself, and then you can visualize this whole thing flipping over so that this A ends up right in the middle of there. You should be able to sort of see that this has to be B prime, this B prime has to be connected to C prime, and C needs to be connected to D, which means that this has to be A. So, if that's all the work you showed because you were able to sort of visualize where everything was going, then that's fine. But for a lot of you, you're probably going to want to trace a couple points manually using that original method, right? Where I went over 1, 2, and then down 1, and then over 1, 2, and then down 1 to make sure that I was on a straight line to connect the original B to the new point, B prime. Either of those methods is perfectly fine. Okay, so we've already discussed that that's how we rotate this particular object. So it has rotational symmetry. Okay. Now, does it have line symmetry? Is there a line that we can draw through this entire Cartesian coordinate system here that if we treated it as a mirror, are all the points going to line up with an existing point on the other side? So in this case, you can see they already drew it for us. The line that represents our symmetry is this line right here. Okay. Now, how do I know that? We don't necessarily have to line up. We're not rotating the object, so we don't need to worry about, does A prime match up with A? Does A on one side match up with A prime on the other? C, D. We don't have to consider that as much. What we have to consider is, for every point on the left side of this object, is there a point on the right side object that is equal distance away from that line? So let's check B, and I'll use a red line to check B. So B is 1, 2 horizontal moves away from the blue line, which means if I have a point that's 2 horizontal on the other side, we're on our way. So that point checks out. Okay, now clearly C is going to be the exact same thing, right? C is 2 units away from that line. If I go the exact same 2 units on the other side of the line, it matches up. How far away is A? Well, I'll just do it up here. A is 1, 2, 3, 4, 5 away from the line. So 1, 2, 3, 4, 5 is right there. So that lines up, and you know that D is going to line up too. Okay. Now, a lot of times you can just look at it and sort of determine, is this going to work out or not? And most of the time you'll be right. So let's see, what's this one? So C lined up with that one, B lined up with that one, A lined up with that one. I need one more color. D's going to line up with that one. So that means we do have line symmetry on this one as well. We had both rotational symmetry and line symmetry. And where do we have line symmetry? The only place that we can draw the line where it actually works out that way is -1 on the x-axis. So if you wanted to, what is -1 on the x-axis? Okay, that's x equals -1, right? There's no other x value. Y can be whatever you want, but that is the equation for the line. And we know that x equals, without a y, is going to be a vertical line. And then if we had something that was y equals, say y equals 4, that's going to be a horizontal line, right? If we go to where 4 is, 1, 2, 3, 4, then that would be a line that would be something like that. That would be a horizontal line. So that's a review from Unit 4 when we were talking about linear relationships. Do we have an x? Do we have a y? Do we have both of them in our equation? Because that'll be the determinant of whether it is a horizontal graph, a vertical graph, or an oblique graph. Okay, now, there's no rules about this other than what you end up with. You may have symmetry, you may not have line symmetry. You may have rotational symmetry, you may have both rotational and line symmetry. you have to sort of test it to see. You have to do both of those tests that we did up here, number 1 and number 2, to see if we have those. And a lot of times you can just look at it and sort of determine it, but you could also use those steps and little line drawings to figure it out. Okay, so let's look at these 3 rectangles, and let's see if I can get from the black version of these objects, okay, there's the black version of these rectangles, to, I'll just call them the green versions. And how, if we are able to, and I don't know if we are, but if we are able to, how are we able to either reflect the black image or rotate the black image so that it ends up perfectly over top of the green image? Okay. Can we do it? Can we do it? All right, well, let's look at A first. Okay, now let's check. Okay, let's check first if we have rotational symmetry, which means can we rotate this object around a point to make it end up right on top of the other one? Okay, now it looks like we can. Okay, let's just say I took point B, okay, and I just draw a line from B to H. It looks like it can go through that point 180 degrees and end up where we needed to end up. Now, is that correct or not? I just got to sort of track it here. If B ends up there, 2, down 1. No, that's not the right line, and I'll show you why. Okay? I drew the line just because I eyeballed it and thought it looked right, but here's how we know it's not quite right. So if I go B over 1, over 2, and then down 1. So I went from B, okay, the steps I took, I went 2 right, and then I went 1 down. So I need to be able to do that from this external point, which I'm just going to call X. Okay, so if I go 2 right and 1 down, 1, 2, and then 1 down, that gets me to what I think is point B prime. Okay, that's fine, that lined up nicely. Does the same thing work for C though? Okay, so let's check C, and you'll see why it doesn't work. Okay, so if I go with C point, C only needs to go 1, 2 over to get to the, in order to get to the X point, and now I got to go 1, 2 over. Oh, it does actually. So that does line up there. That point right there does end up being C prime. C prime and B prime are connected, so that's great. And then we know that B has to be connected to A, so that's the only way that B can be connected to A is by making this A prime or G. And then we also know that B is connected to C, B is connected to A is connected to D, so the only place that D prime could be is over here where they originally called it F. So I can get rid of those, but I know, okay, that I can rotate this object just using those steps that I just showed you, and I can take the original black object, and as I initially thought I proved myself wrong, but I actually proved myself right. As I initially thought, if we go through this point right here on a straight line, and we're essentially rotating this entire object 180 degrees, I will end up with a situation where A, B, C, D will line up perfectly over top of E, F, G, H, which means that A has rotational symmetry. Great. And we even got a little bit more specific. We said if you rotate this object 180 degrees, you will end up with on top of the green version. So that's great. It has rotational symmetry. Does it have line symmetry? Line symmetry, we're looking at reflection. Can I draw a line somewhere so that all the points match up? And I'm not thinking that there is line symmetry on this one. Okay, now let's just get rid of these lines here, just so I don't have a whole lot of clutter. Okay, so now let's look at, is there anywhere that I can draw a line where all the points are reflected perfectly from one side of the line to the other? And sometimes it looks like you can, but then you got to track it and you see if it actually works out or not. Now, any line like this isn't going to work because point B would take 2 steps over to the line, 2 steps over, and you'll notice that that point exists nowhere on the green line or on the green shape. So that line there, that clearly doesn't work. So a vertical line doesn't work. A horizontal line clearly doesn't work. There's nothing I can draw horizontally that's going to make a mirror. The only line that looked like it might work for a second is a line that goes right. Would be a line that went right here. Is that line a good mirror? Okay. So I need to draw from each of these points a 90-degree angle. Okay, so I just need to go from C to the blue line at a 90-degree angle, which would be like this. That's 90 degrees. Okay? And I need to do the same thing on the other side of the line. So if I go 1 unit 90 degrees on the other side of the line, I end up right here. Well, clearly that point is not on the graph. Okay, so that's not going to work. Okay, and then if we drew, and you'll find the other points the same thing, right? If I draw a 90-degree line for B, okay, I would need to end up down here somewhere, and that doesn't match up with anything on the green. So clearly that doesn't work. And if you looked at it kind of a different way and you thought, oh, well, maybe I drew it the wrong way. Maybe I should draw it, which way did I draw it? That way? Maybe I should draw it this way instead. Is there a way that I can draw a line here where I can reflect it? And you'd find the same thing. You have to go from a 90-degree, so your B point would need to be there, okay, and your C point would need to be there somewhere, so that isn't going to work. So it doesn't matter where you try to draw the line. There's no place you can draw it where it has that line symmetry. You can't make a reflection. It just doesn't work. There is no line symmetry. Can't make a reflection. There's no way I can draw a line to make it happen. Okay, now let's look at B. For test number 1, does it have, does it have rotational symmetry? Is there a way for me to rotate this object so every point ends up on, every point on the black object ends up on the green object? And yes, there is. I think it's pretty obvious that if you do a line that connects B and H, okay, you do a line that connects B and H, that will end up with rotational symmetry. So if I just go over 1, okay, so go over 1 and then down a half, it looks like. Okay, then I go over 1 and down a half, I get to the H. So that works out perfectly, which means if you flip this entire object 180 degrees again, you are going to end up with your B prime point here, which is H. Okay, and then we know that B has to be connected to A on the long, so that would be A prime, or G. Okay, we know that B has to be connected to C, so this would be your C prime, and then that leaves your D prime down there. Okay, they called it H, E, F, G, but I'm just showing you how each of these points would move. The A would have to come all the way over and down, but it's still on a straight line. Like the line through this point right here, it's still a straight line, right? Like it'll still end up on a straight line. I just try not to clutter things too much. So that one clearly does have rotational symmetry. And once again, it's 180 degrees, right? It can rotate 180 degrees. So it has rotational symmetry. We're 2 for 2 on rotational symmetry. Does it have line symmetry? In this case, this one actually does. If I get rid of my lines that I used to check for rotational symmetry, just get rid of the clutter. My original object was black. And we're checking to see if it'll reflect on a line so it ends up on the green. And this one is pretty easy to see. It is pretty easy to eyeball it. Clearly, if you put a line right there, you don't have to have arrows, it's just a line. Can have arrows, but doesn't need it. Clearly, every point from the top object can end up on the bottom object if you trace it out. So if I start with point B, it's 1 jump down to the line vertically. So if I go 1 jump again, I end up right there. So this point ends up there. Okay, let's check point C. It's the same thing. It's 1 jump to the line. It's 1 more jump down to the H point. And then we could do the rest. If I go down 1, 2, 3, 4 on A, and then I go down 1, 2, 3, 4, I end up there. Okay, so every point on the top, if you move the same distance to hit the line of symmetry, and then you do that same distance again, every one of those points lines up perfectly. So this one has line symmetry as well as rotational symmetry. So has line symmetry. So this one had both, okay, which leaves us with our last question here, which is, I mean, it's the same question. We're just going to run our tests again. Do we have rotational symmetry? This one's pretty obvious to see. Yes, we do, right? If I just take a line from the middle of AB and draw it down there, and I draw a 90-degree angle, okay, clearly that line AB, okay, that 90-degree angle right there is going to take the middle of the AB line and make it the middle of the FG line. So instead of FG, this is really A prime, B prime. We know that B is connected to C, and we know that A is connected to D. So A prime, B prime, C prime, D prime is really the second object they drew, which was FGHE or EFGH, if you want to do it in alphabetical order. But it's very, very clear that it does have rotational symmetry. If you just rotate the object 90 degrees, you are going to end up taking the black object and you're going to end up right on top of the green object. So has rotational symmetry. And if you wanted to be specific, you could say you could either rotate this object 90 degrees clockwise or counterclockwise, but you will get, whether you do a positive or negative, you will end up with your black overlaying your green. So it does have rotational symmetry. Does it have line symmetry? It doesn't. It's an overlapped object. There's clearly no line I can put anywhere on here where you're going to have a point that is equidistant from the line as something on the other end. So one point might match up or something, but you're not going to be able to match up anything else. So I don't believe that there's any way that you can do anything other than rotate that and get the rotational symmetry, but there's no way that you're going to be able to reflect that. So there would be no line symmetry, at least in our universe, that would allow us to reflect an overlapped object on itself. So first one had rotational symmetry but no line symmetry. The second one had both rotational symmetry and line symmetry. The third one, very much like the first one, had rotational symmetry, but it did not have line symmetry. So we could just run those tests on any question that asks you if two objects are related by reflection or by rotation, and you can determine if that is the case. Okay, so the number 2 here is just quick examples of how do we do these transformations, these rotations. So let's just do them one by one here. Let's start with the red object, and we'll end up with let's say we'll put it in green. Okay, so a rotation of 180 degrees about the origin. Well, you have to know what the origin is first. The origin is 0.00, which is clearly where those two black lines are going to intersect. Right, that's the y and that's the x. So this is point. Let's just call it point O for origin. Now I want to rotate this object around that point. So basically I want to stick a pin in this and rotate it 180 degrees. So how am I going to do that? Why don't I start with point A? Okay, I'll start with point A and I'll see how does point A relate to point O? Because I need to rotate this in a straight line, which means it has to be somewhere on that line right there is where my new A point has to end up. It's easiest, I think, if you just try to find out what do I need to do to get from point A to point O and then replicate it, right? So from point A to point O, I have to go over 1 and down 1. So I have to go over 1 and down 1 again from point O, and then I get point A prime. So that, I think, is the simplest way of determining where that A point will end up. Okay? And you can use the same process for other points, right? Now let's look at D. So for D, maybe I'll do that one in purple. Okay, so for D, how do I get to point O? I have to move 1 to the right. Great, so I just move 1 to the right again, and I should get to D prime. So that's great. That was super easy. And D and A are on the short end here, and you'll see they are also on the short end there. So what about point B and point C? Okay, point B is going to be in blue. So point B, how do I get from B down to O? I have to go down 1. Okay, so there's 1, and then I have to go 1, 2, 3 to the left. So it would be down 1 and then 3 to the left. So I just do that again. So I go down 1, and then I go 1, 2, 3 to the left, and that's where B prime has to be. B prime, and then D, you could trace it out, but it doesn't really make much sense. You know that, C. You know that C has to be connected to B, so this has to be C prime right here. Okay. So now to put it all together, and what does the new object look like? Okay, connect my A point, A prime to my B prime, to my C prime, to my D prime, and my new object looks like that. And it didn't take very long for me to track each of those points. You probably didn't need to track anything more than 2 points to figure out where every other point was going to lay. So that is how you would rotate that object. Okay, now a reflection of A, B, C, D in the x-axis. This one's super easy. Whenever you're trying to reflect along a horizontal line or a vertical line, and the object is touching that line, it becomes very easy to reflect. Because you know each point just has to be the same distance away from your line of reflection. So in this case, our line of reflection, they told us, was the x-axis. Okay, well, what's the x-axis? Okay, the x-axis, whoops, didn't mean to do that. The x-axis is, there we go. The x-axis is right there. And of course, I've made the color black, which is the exact same as the original, so I'll just change that to blue. Change that to blue. There we go. So I didn't really need to draw that line. I was just indicating that it is the exact same line as the x-axis. Okay, so that is the x-axis right there. Okay, or if we wanted to treat it as, what is the equation of that line? The equation of that line would be y equals 0. Because it doesn't matter what value of x you use, 1, 2, 3, 4, 5. Y is always going to be 0. It's neither positive nor negative. It's the line going right through the origin. So it's very, very easy to reflect these because you just need to take each point and then push them the exact same distance on the other side. So if I look at B, it's 1 unit away from the line, so in a vertical manner. So it has to be 1 unit away from the line in a vertical manner. Line C is touching, or point C is touching the line, so it doesn't have to move at all. Point D is touching the line, it doesn't have to move at all. And point A moves the same as B. It's 1 unit away from the line vertically. So if we put it on the other side, 1 away from the line, we get our reflected object. So that one was pretty easy. And you know, it would have been the same thing if it had been, say, take this square and reflect it on the y-axis. You would be like, okay, well, it's already touching the y-axis, so these 2 points are already there. Now I just need to bring that point there and that point there, and then I'd have a reflected object in the vertical. So when they're touching the axis, or it's a horizontally oriented object or a vertically oriented object, tends to be very, very simple to do those transformations. Okay, the last point here is something called a translation, and translations are probably the easiest part of this unit. It's going to use R for right, L for left. I think you see where this is going. U for up, and D for down. And all we're doing when we're translating objects for these examples is we're just moving the entire object. You don't have to rotate anything. And rotations, I feel, are a lot more difficult to visualize than just picking an object up and moving it. So students typically don't have any difficulty with this at all. We've got our original object, our PQRST, and it's going to tell us how it wants us to move things. So the first one for A is a translation of L2, which means it's going to move left 2 units. So all you need to do is take every point and move it left 2 units. And you don't need to do more than 1 point in order to figure it out. Let's just start with P. I want to move it left 2 units. There's 1 unit, there's 2 units, so P prime goes there. And the object doesn't change size, it doesn't change shape, and it doesn't rotate, which means as soon as you got 1 point, you probably can just fill in the blanks for the rest. I just picked that entire object up and moved it over. The point that used to be known as S is now going to be R prime. Okay? The point that used to be T is going to be Q prime. T bounces over here, it becomes T prime, and S bounces over here and becomes S prime. So you can see that this is not particularly difficult doing these vertical and horizontal translations because you don't have to change the shape, the size. You just have to pick the entire object up and move it and make sure that you've got all the points in the right spot. The next one is, a little bit more complicated, but not really. It's left 2 and down 3. So each point goes left twice and down 3 times. So left 2, down 3. Let's start with the P again. 1, 2. There's the left 2. Now the 1, 2, 3, which means my P prime ends up right there. And then again, the object does not change size or shape. So why don't I just draw the object, as long as it's oriented in the grid in a way that makes it easy for me to sort of visualize it. I picked it up, I moved it over 2 units, and I moved it down 3 units. And I ended up there. My points are all going to be in the exact same order that they were before. I'm just going to make them primes instead to indicate that it's the translated version. So there you go. That should give you a bit of practice working with line symmetry as well as rotational symmetry, and then rotating and reflecting objects, simple shapes, by lines or points that are outside of the original object. So instead of just spinning an object from a corner or from the middle, now we're going to spin an object around an external point. All right, good luck with this. Let me know if you have any questions.